This is a good review question for the test that's coming up. We're looking at the limit as x is approaching infinity of the square root of x squared plus 36 minus the square root of x squared minus 1. If we go in and do our direct substitution, we get the form of infinity minus infinity. That's one of those indeterminate forms that doesn't tell us anything, and we need to go back and we need to manipulate it. And so the trick to manipulate this one is to multiply by a fancy one, and that fancy one is going to be the conjugate of what we have, what we're taking the limit of. So let's do that. Maybe we can do that on the side right here. So we're going to multiply, that fancy one is going to be the square root of x squared plus 36. Outside of the radical is plus, and then another square root underneath that radical is x squared minus 1. And so when we distribute to the numerator here, think of this as difference of squares. So we're squaring that first term, and squaring that first term is just going to give us what the radicand was. And so doing that, we get x squared plus 36 minus, and now we want to square that second piece, that square root of x squared minus 1 by the difference of squares. Well, that's going to get rid of the radical. And so we're left with, we need a parentheses there, x squared minus 1 inside the parentheses, all over x squared plus 36 plus square root of x squared minus 1. So simplifying this, if I distribute my -1 inside that parentheses, I notice I get an x squared minus x squared cancels, and I have a 36 minus a -1, so 36 plus 1, which is 37, all over my denominator. And so now when we go in and we plug in infinity, wherever we see an x, notice that the denominator is blowing up. And so some number, some constant over something that's blowing up and getting bigger and bigger and bigger, and this is going to 0.
Okay, yeah, I don't know why I forgot how to do that, but yeah, thanks for the clarifying.
Yeah, no worries. So in this example, it says find dy. We're given 2y raised to the 7/2 powers plus x times y minus x equals 0. This is in implicit form. It doesn't have, it's not an explicit equation y just in terms of x. And so when we go through here, we're going to use implicit differentiation, and whenever we take the derivative with respect to y, we're going to tack on that dy dx. And so let's look at the first term, 2y raised to the 7/2. So if I bring down that power, I'm going to have 2 times that power of 7/2. Y, subtract 1 from that power. So 7/2 minus my common denominator is 2. So 7/2 minus 2/2, that gives me 5/2 dy dx. Plus, and so now when I take the derivative of x times y, I need to use the product rule. So the derivative of x is just 1 times the times y plus x times the derivative of y. So the derivative of y is 1, but it was with respect to y, so dy dx. Minus the derivative of x, which is just 1, equals the derivative of 0, which is just 0. So let's just group the terms together that have the dy dx on one side of our equation. Let's get every other term that doesn't have the dy dx. Let's just leave it on this left-hand side. And so I notice that we're going to have to subtract y on both sides. And we're going to have to add 1 to both sides. And if you're okay with it, let's pull out the dy dx that we have in common with both of those terms. And before we do that, let's just cancel this 2 and this 2 together. So pulling out a dy dx from that first term, this first grouping, all we're left with is that 7 and a y raised to the 5/2. Now, when we factor out dy dx from this x times dy dx, all we're left with is that plus x. And this is equal to, we added 1 and subtracted y. I'm just going to write it as 1 minus y. So we're almost done. We want to get dy by itself. Actually, before we do that, let's divide both sides by that parentheses. So we have dy dx by itself. So we have dy dx is equal to 1 minus y all over 7y to the 5/2 plus x. Now let's think of it as multiplying both sides by dx. And so we get dy by itself. So dy is equal to this 1 minus y all over 7y to the 5/2 power plus x, and that's all times dx. So we have find dy for y equals -2 cotangent of, in parentheses, think of this as this 3x to the 7th over 7. So we don't need to use implicit differentiation on this one. So taking the derivative of y, we're just going to write it as dy dx though, is equal to -2. So I need to use my chain rule. My outer function is that cotangent. And so the derivative of cotangent is negative cosecant squared. Of the inside, so I have this 3x to the 7 over 7, all times the derivative of the inside. And so if I take the derivative of the inside, bring my power down front, I notice that's going to cancel with my 7 in the denominator there. And so I'm going to have 3 just left in front, x, and subtract 1 from my exponent. So to the 6th. I'm going to multiply both sides by dx. And so we get dy is equal to, and just so we aren't confused, we are going to move this in front and multiply it by 2. And notice we also have 2 negatives. So 2 negatives make that positive. So I'm going to do 2 times 3x to the 6. That gives me 6x to the 6. All times my cosecant squared of my argument 3x to the 7th over 7. And we multiplying both sides by dx. So this all times dx.
That seems super simple.
It's not too bad if you have that. So one more problem to look at. It says find a linearization that will replace the function over the interval that includes the given point x sub 0. Center the linearization not at x equals 0, but at a nearby integer x equals a, at which the given function and its derivative are easy to evaluate. Well, cubed root of, and we have f of x equals the cubed root of x, and x sub 0, which we're trying to approximate, is the cubed root of 216.4. The cubed root of 216 is 6. And so we can choose our a value to be 6. we're going to let our A value be 216. And so we need to look at what is f of 216. And so the cubed root of 216, this is equal to 6. We need to figure out what the derivative of f of x equals the cubed root of x is, and I'm going to just rewrite it as f of x equals x to the 1/3. And so when we take the derivative of f of x, bring down our power, subtract 1 from our exponent, so 1/3 minus 3/3 is negative 2/3. Let's clean that up and bring it down to the denominator and make the exponent positive. And so we have 1 all over 3, and this is the same thing as a cubed root of x, quantity squared. And so now let's evaluate this when x is a, which is 216. So going in and plugging in 216 wherever we see an x in our derivative function, we have 1 over 3 cubed root of 216 quantity squared. So this gives us 1 all over 3. Well, the cubed root, again, of 216 is 6, and then we're going to square our 6. So we have 1 over 3 times 36. 3 times 36 is 108. So our derivative of 216 is 1 over 108. Our linearization equation is f of 216 minus, or not minus, plus f prime of 216 all times x minus 216. Well, f of 216 we found to be 6, plus f prime of 216, which we found to be 1 over 108, all times x minus 216. When it asks for the linearization, set the center of the linearization at x equals, choose the value that we know how to evaluate if we plug that number back in here without a calculator. And so in this case, our x value is going to be 216. And our linearization problem, like I said, we just found, is this L of x equals 6 all over 108 times the quantity x minus 216.